row space, column space, and rank of a matrix. So suppose you have a data frame. If you're familiar with Python, machine learning, deep learning, you know a data frame is basically a table, but we can use some nice functions and methods to work on a data frame much more easier and nicer. So here you have two variables, feature 1, feature 2, with some data point. So each row corresponds to an observation or data point, and each column corresponds to a feature or variable. The row space of this matrix is the span of its rows. It captures the essential information about the observations in the dataset. And if you try to write the third row as a linear combination of first two rows, you're going to be successful. In this case, the dataset lies in a lower dimensional subspace because the third row can be expressed as a combination of the first two rows, everybody. Why it is important? In the context of machine learning, this scenario happens when there is redundancy or linear dependence among features. Identifying such relations can be helpful for reducing dimensionality or understanding which features or variables basically contributes the most to the variability of dataset. For an m by n matrix, recall that n tuples correspond to the rows of A, and they are basically row vectors of matrix A. So a matrix is a rectangular array with m rows in this case and n columns. So if you take this matrix and take the rows of this matrix, you can basically define row vectors of matrix A. The very first vector, A sub 1 and 1, A sub 1 and 2, A sub 1 and n. The second vector, A sub 2 and 1, A sub 2 and 2, A sub 2 and n. And you can continue this process, get A sub m and 1, A sub m and 2, and A sub m and n. These are row vectors of matrix A. With the same argument, you can define the column vectors of matrix A. Just take the columns and list them all. The column vectors of the matrix, the first column, represent the first vector, A sub 1 and 1, A sub 2 and 1, and A sub m and 1. The second column is the second vector, A sub 1 and 2, A sub 2 and 2, and then A sub m and 2. And you can list them all, and finally you have A sub 1 and n, A sub 2 and n, and A sub m and n. So why it is useful for us? If you have an m by m matrix, then the row space of A is a subspace of the n space. It is going to span by the row vectors. You can also define the column space. The column space of matrix A is the subspace of M space, which is spanned by the column vectors of A. Well, if you have matrices that are row equivalent to each other, they're going to have the same row space. If A is an m by n matrix, and it is row equivalent to an m by n matrix like B, then the row space of A is the same as the row space of B. And again, remember, the row space is a subspace spanned by rows. Column space is the subspace that is spanned by the column. So all you need to do, you can take a matrix and apply elementary row operations and write the row equivalent matrix to that original matrix and find all non-zero rows or non-zero columns and then work with that subspace. And remember the elementary row operations, interchanging two rows, multiplying a row by a non-zero constant, and finally, the last one was adding a multiple of a row to another row. We have a nice theorem. If you have a matrix like A which is row equivalent to matrix B, in row echelon form, then the non-zero row vectors form a basis for the row space of A. So if somebody asks you, hey, find the basis for the row space, you're going to say that, okay, first I'm going to write down A, and then I'm going to apply elementary row operations to find a matrix that is in row echelon form. And I'm going to count the number of non-zero rows, and then I'm done. Those are going to be the vectors in the basis. Find the basis for the row space of this 2 by 2 matrix. Okay, 2 by 2 matrix. It doesn't seem that difficult. Here, I'm going to apply elementary row operations and write this matrix in row echelon form. This matrix can be reduced to 1, 0. The pivot is 1, so we're not going to change this. We're going to copy down the first row. But here, you have a 2. You have to multiply the second row by a half or divide the second row by 2. It becomes 0 and 1. How many non-zero rows do you have? You have 2 non-zero rows. So the basis for the row space is this set, including the first vector, 1 and 0, and the second vector, which is 0 and 1. Here we go. We found the basis for the row space of this matrix. It means that the dimension is equal to 2. If you're working with the vector space, the dimension becomes 2. Later on, we're going to introduce the rank. So you're going to see what a rank is.